The universe holds secrets that defy even our greatest scientific minds. We are diving into the deepest cosmic mysteries that refuse to stay solved, from the invisible grip of dark matter to the mind-bending paradoxes of black holes. By the end, you will see why some questions about the cosmos might never have final answers. What if everything we think we know about space is only a fraction of the story? What does it truly mean to confront the infinite? Infinity is not a number you can count to, not a distant point you can reach. It is a concept that shatters our everyday understanding of reality. We are wired to think in finite terms, to see a horizon, but the universe operates under a different set of rules, and infinity is perhaps its most baffling. Mathematicians have tools to work with it, but our brains simply cannot picture something without end. This is not just a philosophical puzzle, it is a concrete problem for astrophysics. Our most powerful theories, the very equations that describe the birth of the cosmos and the fabric of space-time, are filled with infinities. They pop up in the equations for black holes, where density is predicted to become infinite at the singularity. They appear in quantum field theory, requiring clever mathematical tricks to subtract them away so we can get answers that match our experiments. Cosmologist Brian Greene has called infinity both a necessary tool and a profound torment for this very reason. We need it to make the math work, yet its presence often signals that our understanding is incomplete, that we have reached the edge of a theory. This challenge becomes even more pronounced when we consider ideas like the multiverse. If eternal inflation is true, then our entire observable universe is just one bubble in a frothing, endless sea of space, constantly giving birth to an infinite number of other universes, each with potentially different laws of physics. How do you even begin to test such a concept? How do you prove an infinite reality? Infinity forces us to ask if some cosmic questions are beyond the reach of science, not because we are not smart enough, but because the answers are, by their very nature, unreachable. This foundational struggle with the boundless sets the stage for every unsolved mystery to come, starting with the most famous paradox of all. We are surrounded by a ghost. It does not reflect light, it does not absorb it, and it does not emit a single photon for our telescopes to catch. Yet this phantom substance, which we call dark matter, makes up the vast scaffolding of the cosmos. It is the hidden architecture of the universe, an invisible skeleton holding galaxies together. Without it, the grand spirals we see would simply fly apart. The story of dark matter begins nearly a century ago with an astronomer named Fritz Zwicky. He was studying the Coma Cluster, a massive group of galaxies, and he noticed something bizarre. The individual galaxies were moving so fast that the gravity from all the visible stars and gas should not have been enough to keep the cluster from flying apart. It was as if the cluster was held together by the gravitational glue of something he could not see. He called this missing material Dunkel Materie, dark matter. For decades, his idea was largely ignored. Then, in the 1970s, astronomer Vera Rubin provided stunning confirmation. She meticulously charted the rotation speeds of stars in distant spiral galaxies. According to the laws of gravity, stars on the outer edges of a galaxy should move slower than those near the center, just as Pluto orbits our Sun more slowly than Earth. But Rubin found something that defied this logic. The stars at the edge were moving just as fast as those near the core. The only possible explanation was that each galaxy was embedded within a massive, invisible sphere of matter, a halo exerting a gravitational pull on everything within it. This matter is not just a little bit of missing stuff, It outweighs all the ordinary matter, every star, planet, and nebula, by a factor of about 5 to 1. It is the dominant form of matter in the universe, so what is it? The leading idea is that it is a new type of elementary particle, one that rarely, if ever, interacts with light. Physicists have proposed candidates with names like WIMP, weakly interacting massive particles, or actions, hypothetical ultra-light particles. To find them, scientists have built incredibly sensitive detectors placed deep underground in old mines, shielded from cosmic rays, waiting for the incredibly rare bump of a dark matter particle passing through. Others look for the faint signals of these particles annihilating each other in space. But so far, after decades of searching, the detectors have remained silent. This relentless absence is itself a profound clue. It tells us that dark matter is not just hidden, it is profoundly other. It operates by rules we do not yet understand, suggesting that our standard model of particle physics, for all its power, is incomplete. It describes only the tiny fraction of the universe that is visible to us. The hunt for this invisible enigma forces us to confront a humbling possibility that most of the cosmos is built from something we cannot see, touch, or currently comprehend. And if the mystery of dark matter is what holds the universe together, then its counterpart, dark energy, is the force determined to tear it all apart. But the universe's hidden architecture is only half the story. Just as we discovered the invisible glue holding galaxies together, we stumbled upon a force determined to tear everything apart. In the late 1990s, two teams of astronomers were measuring the distances to faraway supernova, expecting to find proof that the universe's expansion was slowing down due to gravity's relentless pull. Instead, they found the exact opposite. The most distant stellar explosions were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe was not slowing down, it was speeding up. Some unknown force was pushing galaxies apart at an ever-increasing rate. This shocking discovery earned the teams a Nobel Prize and introduced the world to dark energy, a repulsive force that makes up about 68% of everything in the cosmos. It is the majority ingredient in the universe's recipe, and we have no idea what it is. The leading candidate is something Einstein proposed and then later rejected, calling it his biggest blunder, the cosmological constant. This is an energy inherent to the fabric of space itself. Even in a perfect vacuum, empty space would still possess this faint, repulsive energy. As the universe expands and more space comes into existence, more of this energy appears, causing the expansion to accelerate faster and faster. But the math presents a huge problem. Our best quantum theories predict a strength for this vacuum energy that is wrong by a factor of 1 followed by 120 zeros. It is perhaps the worst prediction in the history of physics. This colossal failure suggests we are missing something fundamental, a deep flaw in our understanding of quantum mechanics and gravity. Other theories suggest dark energy is not a constant but a dynamic field that changes over time, a new kind of force that could weaken or strengthen. This uncertainty leaves the ultimate fate of the universe hanging in the balance. If dark energy remains constant or grows stronger, it could eventually lead to a big rip where every galaxy, every star, every planet, and even the atoms themselves are torn apart by the accelerating expansion. If it weakens, gravity could finally regain control and pull the universe back together in a fiery big crunch. As physicist Adam Rees has emphasized, dark energy forces us to reconsider the most fundamental constants of nature. It is a reminder that the laws we take for granted might not be so constant after all. This mysterious pressure woven into the void dictates the destiny of all things. And if we want to understand the most extreme forces shaping our cosmos, we must venture to the places where the fabric of reality breaks down completely, to the edge of a black hole. Deep within the gravitational heart of a black hole, the known laws of physics cease to exist. This is a point of infinite density, a singularity where the fabric of spacetime is torn apart. The boundary surrounding this cosmic abyss is the event horizon, the point of no return. For decades, the story was simple. Anything that crosses this threshold is lost forever to the universe. But then Stephen Hawking changed everything. He discovered that black holes are not entirely black. Due to bizarre quantum effects happening just outside the event horizon, they slowly leak a faint glow of particles, now known as Hawking radiation. This radiation carries away energy, causing the black hole to gradually shrink and over eons evaporate completely. This brilliant insight created one of the most profound conflicts in modern science, the black hole information paradox. Quantum mechanics, the rulebook for the subatomic world, has one unbreakable law: information cannot be destroyed. Every particle carries information about its properties, and that information must always be preserved, even if the particle itself is annihilated. You could, in theory, reverse time and see where every piece of a scrambled egg originally came from. But general relativity says that all the information about whatever fell into the black hole is trapped inside, and when the black hole evaporates, it vanishes forever, leaving behind only the random thermal glow of Hawking radiation. It is the ultimate cosmic delete button. So, which is it? Is information permanently lost, violating quantum mechanics, or is it somehow preserved, violating our understanding of relativity? This paradox is so severe that it has forced physicists to propose radical solutions. One of the most startling is the firewall hypothesis. It suggests that the event horizon is not a smooth, empty space as Einstein predicted. Instead, it might be a wall of blazing high-energy particles, a literal firewall that would incinerate anything attempting to cross it. This would solve the information paradox by ensuring the information never actually enters the black hole, but is instead smeared onto the surface of the horizon. But this creates a new problem. It means an astronaut falling into a black hole would not experience the gentle fall of general relativity. They would be vaporized in an instant. So, do we trust Einstein's smooth spacetime or the quantum need to preserve information? Leading thinkers like Leonard Susskind have championed other ideas, like the holographic principle, which suggests that all the information describing a three-dimensional volume of space is actually encoded on its two-dimensional boundary, like a cosmic DVD. For a black hole, every bit of information about what fell in is painted onto the event horizon. When the black hole radiates, it slowly releases this information back into the universe, scrambled but not destroyed. Others speculate about information escaping into another universe or being hidden within a vast cosmic landscape we cannot see. The recent detection of gravitational waves from colliding black holes has added thrilling new data, but it has also deepened the mystery. The way these massive objects merge and ring down like bells provides new tests for our theories, and so far, they have not pointed to a clear winner in this fundamental debate. This struggle to understand a black hole is not just about these cosmic monsters. It is a direct path to questioning the very first moment of existence, the singularity from which our entire universe was born. The singularity at the heart of a black hole is a mirror of our own cosmic origin. We trace the history of our universe backward through time, watching galaxies converge, space contract, and temperatures soar until we reach a point of infinite density and temperature, the Big Bang. This moment, approximately 13.8 billion years ago, marks the beginning of everything we know, the origin of space and time themselves. But the equations of general relativity break down at this singularity, just as they do in a black hole. The theory describes the expansion from this point, but it cannot tell us what caused it or what, if anything, came before. The Big Bang is not the explosion of matter into a pre-existing space. It is the rapid expansion of space itself. This leads to one of the most profound questions we can ask: what happened before the Big Bang? The very question might be a trick of language, as time as we understand it may have begun at that instant. Asking what came before the Big Bang could be like asking what is north of the North Pole. Yet, physicists are not satisfied with this answer. They have proposed breathtaking alternatives. One leading idea is eternal inflation, championed by cosmologists like Alan Guth. In this model, our entire universe is just one bubble in a vast, eternally expanding cosmic foam. The Big Bang was the moment our particular bubble of space began its rapid inflation. Beyond our bubble, an infinite multiverse of other bubbles may exist, each with its own unique laws of physics, each with its own beginning. Other theories suggest a cyclical universe, one that expands, contracts in a big crunch, and then bangs again in an endless cosmic cycle. There is even the staggering proposal that our universe could be the result of a random quantum fluctuation, a temporary bubble of something that emerged from a state of true nothingness. But this idea forces us to define nothing, and a quantum vacuum is not nothing. It is a seething sea of potential. As Guth himself has pointed it out, while inflation explains the remarkable uniformity and structure of our cosmos, it also implies a reality that is far vaster and more strange than we ever imagined. If our universe is just one island in an infinite archipelago, then the quest for a single beginning may be futile. This leads directly to another haunting mystery. Why does our particular island, our universe, seem so perfectly designed for us to be here? This perfect calibration is not just a lucky break, it is a cosmic prerequisite for our existence. The strength of gravity, the mass of an electron, the precise energy in the nuclear bonds that hold atoms together. If any of these fundamental constants were even slightly different, the universe as we know it would not exist. If gravity were a little stronger, the universe would have collapsed back on itself immediately after the Big Bang. A little weaker, and matter would never have clumped together to form stars and galaxies. If the strong nuclear force were altered by even 1%, stars would be unable to create the carbon that is essential for life. Physicist Martin Rees identified 6 of these numbers that seem exquisitely fine-tuned, a set of dials that all had to be set to exactly the right values to allow for a cosmos that is complex, long-lived, and conscious. The odds of this happening by random chance are astronomically small, so small that it forces a profound question. Why is the universe so hospitable to us? One answer is design, that some intelligence set the dials, but for many scientists, this simply pushes the question back a step. Another, more scientific answer is the multiverse. If an infinite number of universes exist, each with its own random set of physical constants, then it is no surprise that we find ourselves in one of the rare universes where the numbers are just right for life. We are not a lucky accident, we are a statistical inevitability in an infinite cosmic landscape. This idea is humbling, suggesting our entire universe is just one possible outcome in a vast ensemble where most realities are barren and lifeless. It transforms the question of fine-tuning from why to where, placing us in a reality that is special only to us, but utterly ordinary in the grand, infinite scheme of things. And if this infinite multiverse is real, it forces us to confront the ultimate manifestation of infinity. This cosmic landscape of infinite possibilities is known as the multiverse. It is the ultimate expression of infinity, a proposal that our universe is not alone but is just one page in an infinite book of realities. Each of these other universes could operate under a completely different set of physical laws. In some, gravity might be repulsive. In others, atoms may never form. This idea does not come from science fiction, but emerges directly from the mathematics of our two most powerful theories, quantum mechanics and cosmic inflation. Inflation theory suggests that the rapid expansion that shaped our universe never truly stops, but continues eternally, constantly spawning new universe bubbles in an endless sea of spacetime. Quantum mechanics adds that these new universes can have random, different properties. This provides a stunning scientific answer to the fine-tuning problem. We do not live in a miraculously tuned universe. We simply live in one of the countless universes where the numbers were right for life to emerge. We are an inevitable outcome of infinity. Physicist Max Tegmark has even created a taxonomy for this mind-bending concept, categorizing multiverses into levels. The simplest level is just our own infinite space, where distant regions contain exact copies of you and me. Another level involves those inflating bubbles with different physics. The most extreme level is a mathematical multiverse, where every conceivable mathematical structure is a physical reality. But this incredible solution comes with a colossal price. If the multiverse is real and everything that can happen does happen somewhere, then how can we ever prove it? The other universes are, by their very definition, beyond our observational horizon. We cannot see them, measure them, or interact with them. This pushes the multiverse to the very edge of science, blurring the line between a testable theory and a philosophical speculation. It becomes a meta-explanation that risks explaining everything and therefore nothing. The multiverse is infinity's greatest challenge to the scientific method, forcing us to ask if some ideas are simply beyond verification. To find a path forward, we must shrink our gaze from the impossibly vast to the infinitesimally small, to the quantum realm where reality itself becomes a blur of probabilities. Yet this infinite cosmic landscape is built upon a foundation we cannot see. To truly understand the universe, from the vast expanse of the multiverse to the singular point of the Big Bang, we must find a theory that can bridge the two great pillars of modern physics. We need a theory of quantum gravity. General relativity gives us the cosmos, a magnificent description of gravity warping the fabric of spacetime to create planets, stars, and galaxies. Quantum mechanics gives us the atom, a bizarre and probabilistic world where particles can be in two places at once. Both theories are spectacularly successful in their own domains, but they are utterly incompatible. When their equations meet, like at the center of a black hole or the moment of the Big Bang, the math explodes into nonsense and infinities. It is the greatest unsolved problem in physics. To resolve this, scientists are building new frameworks from the ground up. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Their different vibrations give rise to different particles, much like a single violin string can produce different notes, but for the math to work, these strings must vibrate in 10 or 11 dimensions. We only experience 3 of space and 1 of time, meaning the extra dimensions must be curled up into a space so infinitesimally small we never notice them. This theory elegantly smooths out the infinities, but it comes at the cost of a dizzying new reality we cannot perceive. Another approach, loop quantum gravity, takes a different path. It suggests that space itself is not smooth and continuous, but is woven from tiny, finite loops, a fabric of discrete threads. Think of a piece of cloth. It looks smooth from a distance, but up close you see it is made of individual threads. In this view, there is no such thing as an infinitely small point. Space has a smallest possible size. This also banishes the dreaded singularity, meaning the Big Bang was not a true beginning but a bounce from a previous universe that had collapsed. As physicist Carlo Rovelli has passionately argued, without a theory of quantum gravity, our story of the cosmos is incomplete. We cannot truly know what happens at the edge of a black hole or the first moment of time. But for all their brilliance, these theories remain unproven. They predict phenomena far beyond our current ability to test, and some, like string theory, predict a staggering multiverse of possible solutions, each with different physical laws. This quest for unification is a direct confrontation with infinity, an attempt to replace the endless with the finite and the measurable, and it forces us to look closer at one of infinity's most puzzling manifestations, the seething, paradoxical energy of empty space itself. The void between stars is not truly empty. It is a quantum sea, a churning ocean of potential where particles and their antimatter counterparts constantly flicker into existence and then annihilate each other almost instantly. These are virtual particles borrowing energy from the vacuum itself for a fleeting moment before vanishing back into the nothingness from which they came. This is not a metaphor, it is a direct prediction of quantum field theory, and we even see its effects in the lab, like the faint shift in the energy levels of atoms known as the Casimir effect. According to the math, this ceaseless activity should fill every cubic centimeter of space with a staggering amount of energy, a force of nothingness so powerful it should have ripped the universe apart moments after it was born. This is the predicted vacuum energy, and yet when we look out at the cosmos, we see something entirely different. The actual energy of empty space, which we measure through the accelerating expansion driven by dark energy, is almost zero. It is there, but it is incredibly, inexplicably faint. The discrepancy between the theoretical prediction and the observed reality is the largest in all of science. The math says the vacuum energy should be a number with 120 zeros after it, but we observe a value so close to zero, it is as if the universe has done a perfect accounting trick, balancing its books to within a hair's breadth of nothing. This is the cosmological constant problem, and it is a screaming alarm bell that our understanding of quantum physics and gravity is deeply flawed. How can nothing be so complicated? Some physicists hope that a theory called supersymmetry might solve it, by having the contributions from different types of particles cancel each other out with perfect precision. But even if that were true, it feels like a workaround, not a true explanation. Others turn to the multiverse and the anthropic principle, suggesting that in an infinite array of universes, we simply live in one where this delicate cancellation happened by random chance, because any universe where it did not happen would be too violent to form galaxies or life. This infinite sea of flickering particles, this energy of the void, is the most fundamental confrontation with infinity we have. It is an infinity born from our equations that the real world refuses to acknowledge. And this battle between the infinite and the infinitesimal may hold the key to one of the most familiar yet profound mysteries of all, the one-way direction of time. The flow of time from past to future feels as certain as gravity, yet the fundamental laws of physics do not dictate this direction. If you were to watch a film of two billiard balls colliding, you could not tell if it was being played forward or backward. The equations work perfectly either way. This is time symmetry. So why does our reality have a clear arrow, a one-way street from what was to what will be? The answer appears to lie not in the laws themselves, but in a single, special condition at the beginning of everything. The universe started in a state of incredibly low entropy, which is a scientific way of saying it was extraordinarily ordered and uniform. Since that moment, in accordance with the second law of thermodynamics, entropy, or disorder, has only increased. This ever-growing disorder is what gives time its arrow. It is the reason you can scramble an egg but never unscramble it, the reason you remember the past but not the future. The increase of entropy is what creates the flow of time we experience. But this only pushes the mystery back one step further. Why did the universe begin in such a remarkably low entropy state? This is the true puzzle. As physicist Sean Carroll points out, a high entropy, disordered beginning would have been vastly more probable. It is as if you walked into a room and found every book perfectly shelved, every paper neatly stacked. The natural state is mess, not meticulous order. So what caused this pristine initial condition? Some theories suggest it was an inherent property of the cosmic inflation that launched the Big Bang, that the rapid stretching of space somehow smoothed everything out. Others wonder if it was a random, incredibly unlikely quantum fluctuation, a statistical miracle that just happened to set the stage for everything that followed. And if the multiverse is real, this question becomes even more dizzying. In an infinite landscape of universes, perhaps most are born with high entropy and remain in a featureless, timeless equilibrium. We simply inhabit one of the rare universes where the arrow of time points forward, allowing for the formation of galaxies, stars, planets, and ultimately, beings who can ponder its direction. The flow of time, then, may not be a fundamental feature of reality, but a local and contingent one, a product of our universe's specific and unlikely birth. This means the ultimate fate of the cosmos, whether it ends in heat death or some other transformation, is written in the conditions of its beginning, a moment we are still struggling to understand. This forward march of time leads us to an inevitable question: where is it all headed? The destiny of our universe hangs on the balance between two titanic forces, the outward push of dark energy and the inward pull of gravity. For a long time, scientists believed gravity would eventually win, slowing the expansion until it reversed in a cataclysmic big crunch, a fiery end where everything collapses back into a singularity. But the discovery of dark energy's accelerating force changed that story. The current evidence strongly suggests a far more lonely and cold fate, something known as heat death. In this scenario, dark energy continues to push galaxies apart at an ever-increasing rate. Over trillions of years, stars will burn through their fuel and flicker out. Galaxies will drift apart beyond the cosmic horizon, leaving each island of stars in utter isolation. Eventually, even the black holes will evaporate via Hawking radiation, and the universe will become a vast, dark, and nearly empty void. The temperature will approach absolute zero and all activity will cease. It is the ultimate victory of entropy, a state of maximum disorder where nothing happens and nothing ever will again. But this is not the only possible ending. Our understanding of dark energy is still in its infancy. What if this mysterious force is not constant but evolves over time? If it were to strengthen, it could lead to a far more violent demise, the Big Rip. In this scenario, the repulsive force of dark energy would overcome not just the gravity between galaxies, but the forces holding galaxies, solar systems, and even atoms themselves together. At a precise moment in the future, every single structure in the cosmos would be simultaneously torn apart. The very fabric of space-time would be shredded. Physicist Lisa Randall and others point out that future observations, like those from the James Webb Space Telescope, are crucial. By studying more supernova and mapping the large-scale structure of the universe with greater precision, we might learn if dark energy is truly constant or if it changes, determining whether our fate is a slow freeze or a sudden tear. This question of cosmic destiny is not separate from the others. It is deeply woven into them. The same fine-tuning that allowed for our existence also set the initial conditions for this eventual end. The arrow of time points directly toward this final state, yet infinity ensures that any prediction is fraught with uncertainty. In an infinite multiverse, perhaps some universes meet a fiery end in a big crunch, while others are ripped apart and still others fade into eternal cold. Our universe's story is still being written, and its final chapter depends on secrets we have only begun to uncover, starting with the very first moment of all. The trigger for cosmic inflation remains one of the greatest unsolved puzzles. We know what this theory does. It explains the universe's incredible smoothness and its slight lumpiness, the seeds for all future galaxies. But we do not know what flipped the switch, what caused the inflationary field, a strange form of energy embedded in space itself, to suddenly activate and send the universe expanding faster than the speed of light. The leading ideas sound like they are pulled from the most ambitious science fiction. Perhaps it was a random quantum fluctuation, a tiny burp in the fabric of reality that was then amplified to a cosmic scale. Or maybe it was a collision between two higher dimensional membranes or brains in the landscape of string theory. Each of these proposals is a shot in the dark, a best guess that highlights our profound ignorance about the true initial conditions of existence. Physicist Andre Linde championed a version called eternal inflation, a self-reproducing process where once inflation starts, it never truly stops. In this model, our entire universe is just one bubble that nucleated in an eternally inflating background. This sea of space is constantly giving birth to new bubble universes, an endless fractal creation where each new realm can have its own unique laws of physics. It is a breathtaking vision, but it is not a complete explanation. It simply pushes the question of a beginning back another step. What started the eternal inflation? Without a definitive mechanism, without knowing what this inflationary field truly is or why it emerged, the theory remains incredibly powerful yet fundamentally incomplete. This is the ultimate initial condition problem, the moment astrophysics confronts infinity at the very origin of everything. And if understanding the birth of the cosmos is difficult, the next mystery is even more personal, explaining why we are made of anything at all. Our very existence is a statistical impossibility. In the first moments after the Big Bang, the universe should have been a perfect balance of matter and antimatter, a symmetrical creation where every particle had its opposite. When matter and antimatter meet, they annihilate each other in a flash of pure energy. According to all the rules, this mutual destruction should have been total, leaving behind a cosmos filled with nothing but radiation, a featureless sea of light with no planets, no stars, and certainly no one to wonder about it. And yet, here we are. For every billion particles of antimatter that were created in that primordial fire, there were 1,000,000,001 particles of matter. That one part in a billion imbalance is the only reason anything made of atoms exists today. It is the reason you and I are here. This tiny, almost negligible asymmetry is the greatest unsolved mystery of our own being, a puzzle physicists call baryogenesis. The question is simple and terrifying. Why was there more matter? The great Russian physicist Andrei Sakharov outlined the three conditions needed for this to happen. The universe had to be out of thermal equilibrium. It had to allow for processes that treated matter and antimatter slightly differently, and it had to violate a principle called charge parity symmetry, which means certain reactions should happen at different rates for particles and their antimatter mirrors. We have found some evidence for this last condition in the behavior of exotic particles, but the effect is far too small to account for the vast cosmic structure we see around us. It is like finding a single drop of water and trying to explain the entire Pacific Ocean. Scientists at facilities like the Large Hadron Collider are smashing particles together at incredible speeds, trying to recreate those first moments of the universe and catch nature in the act of breaking its own symmetry. But as Nobel laureate Jim Cronin noted, the answer might require energies and conditions we can never replicate. A fleeting moment of physics at the very beginning of time that left a permanent mark on everything. This search forces us to confront a profound idea that the entire visible universe, every galaxy and every star, is just the leftover ash from a near-perfect annihilation, the tiny residue of a broken symmetry. The infinite cosmos we observe hinges on a detail so minute it defies belief, a one-in-a-billion fluke that made all the difference. And if the origin of matter itself is shrouded in such mystery, then the source of the universe's most energetic particles is equally enigmatic. These particles rain down from the void with unimaginable force. They are cosmic rays, atomic nuclei stripped of their electrons and hurled across the universe at nearly the speed of light. Most are low energy, but a rare few carry a punch that defies belief, possessing energies millions of times greater than anything we can create in our most powerful particle accelerators, like the Large Hadron Collider. When one of these ultra-high energy cosmic rays slams into our atmosphere, it creates a spectacular secondary shower of particles, a silent firework display signaling an event of staggering power from the depths of space. The mystery is not that they exist, but where they come from. What cosmic engine can possibly accelerate a single proton or atomic nucleus to such insane velocities? The candidates are the most violent places in the universe. Supermassive black holes at the hearts of active galaxies can spew jets of matter stretching for millions of light years. The catastrophic collisions of neutron stars or the explosive deaths of massive stars as gamma-ray bursts release enough energy in seconds to outshine entire galaxies. Yet, when we trace the paths of these ultra-high energy particles back to their source, we often find nothing. No galaxy, no explosion, no obvious culprit. The incredibly powerful magnetic fields that permeate the space between galaxies bend and twist the paths of these charged particles, scrambling their trajectories and erasing their origins. It is like trying to find the source of a bullet that has ricocheted through a hall of mirrors. Physicist Glenys Farrar has pointed to the profound implications of this puzzle. If these rays are not coming from the usual suspects, then perhaps their origin is something entirely new, something we have not yet imagined. Maybe they are the product of the decay or annihilation of dark matter particles, a faint signal from the invisible majority of the universe. Or perhaps they are a sign of new physics, a breakdown in our understanding of how particles interact across vast intergalactic distances. This enigma is a perfect example of how the infinite scales of the cosmos, both in energy and distance, constantly deliver surprises that challenge our models. Just as we struggle to pinpoint the source of these mighty particles, another transient signal from the depths of space arrives without warning, a brilliant and fleeting flash of radio energy that vanishes in the blink of an eye. These brilliant flashes of radio light appear without warning, vanish in an instant, and yet each one unleashes more energy than our sun produces over several days. They are called fast radio bursts, and they are one of the most perplexing signals we have ever detected from the depths of space. Lasting only a few thousandths of a second, their extreme brevity makes them incredibly difficult to catch and even harder to understand. The first was discovered in 2007 by astronomer Duncan Lorimer, sifting through old data from a radio telescope in Australia. It was so powerful and so isolated that for a time, some wondered if it was a glitch in the equipment. But then more were found, confirming these were real cosmic events of staggering power. The central mystery is simple. What natural process can possibly create such an intense, fleeting burst of energy? The leading suspects are some of the most extreme objects in the universe. Magnetars, for instance, are a type of neutron star with a magnetic field so unimaginably strong it could strip the information from every credit card on Earth from halfway across the galaxy. A starquake on such an object, a sudden cracking of its crust under immense strain, could theoretically release a focused blast of radio waves. Other theories point to the cataclysmic collisions of neutron stars or the violent deaths of massive stars. But the plot thickens with the discovery that some of these bursts repeat. They are not one-off events, but seem to come from the same location in the sky again and again, ruling out any kind of destructive collision as their source. This has led to more speculative and far more thrilling possibilities. Could they be the signatures of advanced alien civilizations, perhaps evidence of immense light sails being pushed across the galaxy by powerful radio transmitters? While most scientists consider this highly unlikely, the sheer strangeness of the signals means it cannot be entirely dismissed. As Duncan Lorimer has noted, these bursts do more than just puzzle us, they serve as incredibly useful tools. As the radio waves travel across millions of light years, they pass through the sparse gas between galaxies. This subtly distorts the signal, and by studying that distortion, astronomers can map the otherwise invisible cosmic web of matter that defines the large-scale structure of the universe. So we have a cosmic messenger that is both brilliantly useful and utterly mysterious. The very infinity of possible origins, from mundane stellar corpses to unimaginable technologies, highlights how much violent, transient physics remains hidden from our view. And if the nature of these intense signals is confusing, our understanding of the cosmos faces an even more fundamental paradox: the discovery of galaxies that appear to be missing their most essential ingredient. But the cosmic web is not woven from a single thread. For decades, the invisible hand of dark matter has been the undisputed architect of all galactic structures, its gravitational pull essential for building every galaxy we see. This core pillar of cosmology is now facing a direct and startling challenge. Astronomers have discovered galaxies that seem to be missing this fundamental ingredient entirely. These are not just any galaxies, but diffuse, ghostly objects where the stars move with a slow, lazy grace. Their rotation is exactly what you would expect if only the visible stars were present, with no extra gravitational pull from a massive, invisible halo of dark matter. This should be impossible. It contradicts the very reason we postulated dark matter's existence in the first place. The discovery, led by researchers like Pieter van Dokkum, sent shockwaves through the astrophysics community. It was as if you found a towering skyscraper standing proudly with no foundation, no steel frame, just windows and walls defying gravity on their own. The immediate question was one of error. Perhaps we were mismeasuring the distances to these galaxies, or maybe there was some other hidden mass we could not account for. But repeated observations have only reinforced the anomaly, so if the data holds, we are left with two equally radical explanations. The first is that these galaxies did have dark matter, but it was somehow stripped away, perhaps during a violent collision with another galaxy, leaving behind a skeleton of stars. The second, far more disruptive possibility is that our understanding of gravity itself is wrong. Perhaps on certain scales, gravity does not behave as Einstein predicted, and we do not need dark matter at all. This alternative, known as modified Newtonian dynamics or MUND, has been waiting in the wings for years, and these strange galaxies are its strongest evidence yet. But even MUND struggles to explain all the observations across the universe. we are left in a state of profound uncertainty, a theoretical crisis where the rules we thought governed the cosmos may only be a local ordinance. The sheer number of galaxies in the infinite universe almost guarantees we will find bizarre outliers that break the mold. These dark matter-deficient galaxies are not just cosmic curiosities, they are critical stress tests for our most fundamental ideas. They force us to question whether dark matter is a particle we can find, a property of space we do not understand, or a sign that our grasp of gravity is slipping away. This mystery of what galaxies are made of is inextricably linked to the deeper question of how they all came to be in the first place. Each galaxy tells a story written in starlight and shadow, a narrative of growth and transformation over billions of years. We see the finished portraits, the majestic spirals and glowing ellipticals, but their origin stories remain deeply mysterious. How does a primordial cloud of hydrogen and dark matter collapse into such intricate and varied structures? The broad strokes seem clear. Galaxies grow through two main processes. They cannibalize smaller neighbors in violent mergers, and they birth new stars from their internal reservoirs of gas. But the details are where the infinity of complexity lies. Why do some mergers create a new elliptical galaxy, while others leave a grand spiral intact? Why do some galaxies become star-forming powerhouses, while others, like many massive ellipticals, become dormant red and dead relics? The answers seem to lie in feedback, a complex cosmic cycle of creation and destruction. Supermassive black holes at the galactic center play a crucial role. As they feed on matter, they can unleash unimaginable energy in the form of powerful jets and radiation, heating up the surrounding gas and preventing it from cooling and collapsing to form new stars. This is negative feedback, a way for the black hole to regulate its own growth and the growth of its host galaxy. But there is also positive feedback, where the shockwaves from supernova explosions can compress nearby gas clouds, triggering new rounds of star birth. As astrophysicist Sandra Faber has noted, these feedback mechanisms are the key to understanding galaxy evolution, but they are devilishly difficult to model and observe. Our most sophisticated supercomputer simulations, which incorporate dark matter, gas physics, and star formation, still struggle to create a virtual universe that looks exactly like our own. They often produce galaxies that are too massive or too small, or with the wrong internal structure. This tells us we are missing vital pieces of the puzzle, perhaps some subtle aspect of how energy is injected back into the galactic system. And when you multiply this uncertainty across the 2 trillion galaxies in the observable universe, you are faced with an infinity of unique evolutionary paths, each one a complex dance between gravity, dark matter, and feedback. This grand story of galactic life does not just shape the cosmos we see today, it also illuminates one of its earliest and most dramatic chapters, a period when the first starlight forever changed the nature of the universe itself. For hundreds of millions of years, the cosmos was a featureless sea of darkness. This was the cosmic dark ages, a time when the universe was filled with a thick, neutral hydrogen fog that absorbed any light trying to pass through it. The first stars did not just bring light, they brought a revolution. They were the pioneers of the Re-ionization era, a period when the ultraviolet radiation from these first luminous objects began to tear apart the hydrogen atoms that filled all of space, stripping away their electrons and turning the fog into a transparent plasma. This was the moment the universe became clear, the final major phase transition that allows us to see across the cosmos today. But how did this happen? The first generation of stars, known as population 3 stars, are thought to be the primary architects. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our Sun. burning ferociously hot and bright before exploding in spectacular supernova. Their intense ultraviolet radiation would have been like countless blowtorches, carving out bubbles of transparent, ionized gas in the neutral fog around them. Over time, these bubbles grew and overlapped until the entire universe was reionized, yet we have never directly seen one of these primordial giants. They lived fast and died young, and their light is now stretched into the far infrared by the expansion of the universe, making them incredibly faint. Our best clues come from the other end of this process. By looking at the most distant quasars whose light has traveled for over 13 billion years to reach us, astronomers can study the subtle fingerprints left on that light as it passed through the last remnants of the neutral hydrogen fog. It is like studying a distant lighthouse through a thinning mist. The patterns in the quasar light tell us that re-ionization was not a single, swift event, but a drawn-out and patchy process, likely completed by the time the universe was about 1 billion years old. But the details are maddeningly vague. As cosmologist Richard Ellis points out, the sheer distance and time involved make this a formidable challenge. We are trying to piece together the history of the very first structures in the universe by looking at shadows and echoes from an era that is forever receding from our view. Were the first stars alone responsible, or did early galaxies and their central black holes also contribute significantly? The James Webb Space Telescope is now peering into this ancient era, hunting for the faint glimmers of the first galaxies. Each new observation brings us closer, but the infinity of time that separates us from that foundational epoch ensures that many of its secrets will remain locked away for the foreseeable future. These stellar titans were unlike any sun we see today. They were the universe's first generation, known as Population 3 stars, forged from the pristine hydrogen and helium that emerged from the Big Bang. Without any heavier elements, which astronomers call metals, their formation process was a strange and violent affair. Giant clouds of gas, hundreds of times more massive than those that form modern stars, could collapse directly into a single, monstrous star. The result was a behemoth, burning ferociously hot and blue, with a lifespan measured in mere millions of years before a cataclysmic death in a supernova that seeded the cosmos with the first heavy elements. Everything we are made of, the iron in our blood and the calcium in our bones, was forged in the hearts of these stars or in the spectacular explosions that ended their short lives. They were the ultimate alchemists, transforming the simple primordial universe into a more complex one capable of building planets, and eventually, us. Yet for all their theoretical importance, we have never directly seen one. Their light is stretched into the far infrared by the expansion of the universe, placing them just beyond the reach of our best telescopes. As astronomer Volker Braun has explained, finding them is the holy grail of near-field cosmology. It is a search for our own cosmic ancestry. The James Webb Space Telescope is our best hope, its infrared eyes perfectly tuned to peer back into that ancient era. A confirmed detection would be more than just adding a new class of star to the catalogue. It would be a direct window into the conditions of the infant universe, a chance to test our theories about the very first structures that ever formed. This search also ties into another profound mystery, the case of the missing baryons. Our models of the Big Bang predict how much ordinary matter, protons and neutrons, should exist. But when we add up all the stars, gas, and dust we can see, a significant portion is simply gone. Some astronomers theorize that these missing baryons are hiding in the vast, hot filaments of gas that connect galaxies in the cosmic web, gas that was perhaps heated and dispersed by the violent winds from those first massive stars. The infinity of the past holds the key to the inventory of the present. This missing matter is not dark or exotic, it is the ordinary stuff we are made of. Our most precise calculations of the Big Bang tell us exactly how many protons and neutrons, the baryons, should exist in the observable universe. Yet when we tally up everything we can see, from glittering galaxies to the sparse gas between stars, we come up short by nearly half. It is a cosmic accounting error on a staggering scale, as if someone siphoned away half the atoms in creation. The leading suspect is not some distant dimension, but a diffuse and searingly hot fog known as the warm-hot intergalactic medium. This is the gas that fills the colossal filaments of the cosmic web, the vast scaffolding that connects galaxy clusters across the void. This matter is so hot it emits only faint X-rays, and so sparse that its signature is incredibly difficult to detect. For years, it was purely theoretical, a placeholder in our equations. But as cosmologist J. Michael Shull has described, new tools are finally allowing us to trace its outline. Spectrographs on telescopes like the Hubble use distant quasars as backlights. As the quasar's light journeys billions of light years to reach us, it passes through these faint filaments. Specific wavelengths of that light are absorbed, leaving a unique fingerprint in the spectrum that tells us the composition, temperature, and density of the invisible gas it traveled through. It is like finding the silhouette of a phantom by studying the light that passes through it. Supercomputer simulations of the universe's evolution strongly predict that this is where the missing matter must be hiding, woven into the architecture of infinity itself. This solution, however, only deepens a more profound unease. It demonstrates that even the known ingredients of the universe can vanish into the sheer immensity of space, becoming lost to our senses and challenging our most basic inventories of reality. And if we cannot perfectly account for the matter right in front of us, how can we possibly trust our measurement of the universe's expansion rate, a value that now threatens to tear cosmology apart? This single number, the Hubble constant, is tearing cosmology in two. It is the measure of how fast the universe is expanding at the present time, a fundamental parameter that should be the same no matter how you look for it. But it is not. When we measure it locally by looking at the distances to nearby galaxies and the brilliant standard candles of Type 1, a supernova, we get one answer. This method, championed by Nobel laureate Adam Rees and his team, gives us a precise and robust value. But when we look at the ancient light from the cosmic microwave background, the afterglow of the Big Bang itself, and use our standard model of cosmology to calculate what the expansion rate should be today, we get a different number. The two values disagree significantly, and the error bars are too small to simply shrug it off. This is the Hubble tension, and it is not a small discrepancy, it is a crisis. It suggests that something is fundamentally wrong with our understanding of the universe. As Adam Rees has stated, this is not likely a simple error in measurement, but a hint of unknown physical phenomena. Could it be that dark energy is not a constant after all, but a force that is subtly changing over time, evolving in a way we have not anticipated? Perhaps there is an unknown particle, a relic from the early universe, that is altering the expansion history. Or maybe, and this is the most tantalizing possibility, our bedrock theory of the cosmos, the lambda cold dark matter model, is missing a crucial piece. The sheer scale of the universe is the source of this conflict. We are trying to connect two vastly different epochs, the infant universe and the present day, across an unimaginable gulf of 13.8 billion years. Any tiny, unaccounted-for effect, when stretched across that infinite expanse of space and time, can blossom into a glaring contradiction. This tension is a direct confrontation with the infinite, a measurement challenge so profound it threatens to rewrite the textbooks. And if our understanding of the cosmos at its largest scales is under such strain, then our knowledge of the universe at its very smallest is facing a paradox just as deep. Gravity is the force that sculpts the cosmos, yet it is almost impossibly weak. A simple refrigerator magnet can generate enough electromagnetic force to defy the gravitational pull of our entire planet. This is not a small difference, it is a disparity of staggering proportions, with gravity being weaker than the other fundamental forces by a factor of 1 followed by 40 zeros. Why is the force that holds galaxies together so feeble on the subatomic scale? This is the hierarchy problem, and it suggests that our universe is built on a deeply unnatural foundation. The masses of particles like the Higgs boson should be driven to incredibly high Planck scale values by quantum fluctuations, yet they remain relatively light. It is as if a pencil were perfectly balanced on its tip for billions of years, defying the slightest breeze that should knock it over. This delicate balance seems to require an inexplicable, perfect cancellation of effects, a fine-tuning that makes physicists deeply uncomfortable. To solve this, theories propose radical new ideas. Supersymmetry suggests every known particle has a heavier superpartner, and the contributions from these twins would cancel out the problematic quantum effects, naturally explaining the light mass of the Higgs. But after decades of searching, the Large Hadron Collider has found no evidence for these superpartners. Another breathtaking idea is that gravity only seems weak because it is not confined to our three-dimensional universe like the other forces. It could be leaking into extra, curled-up spatial dimensions that we cannot perceive. In this scenario, proposed by theorists like Nima Arkani-Hamed, gravity's strength is diluted across these higher dimensions, making it appear weak only from our limited perspective. This infinity of possible explanations, from unseen particles to hidden dimensions, shows how the puzzles of the infinitely large cosmos are inextricably linked to the mysteries of the infinitesimally small. It even connects to the bizarrely tiny masses of neutrinos, ghostly particles that barely interact with anything. Each potential solution forces us to reconsider the very nature of reality, suggesting that the weakness of gravity is not a minor detail, but a profound clue pointing toward a deeper layer of physics we have yet to uncover. These ghostly particles slip through our world by the trillions every second, passing through you, the planet, everything, as if it were not even there. They are neutrinos, and their almost complete refusal to interact with matter is matched only by the profound mystery of their mass. According to the standard model of particle physics, the rulebook for the subatomic world, neutrinos should have no mass at all. But we now know they do, an impossibly tiny amount, a whisper of weight that defies all expectations. The lightest neutrino is at least 10 million times lighter than an electron, itself a featherweight particle. This is not just a small detail, it is a screaming anomaly. The standard model has no mechanism to explain such a minuscule mass, which means our most successful theory of particles and forces is fundamentally incomplete. The implications ripple outward, touching the greatest mystery of our own existence. Many physicists, like Janet Conrad, have pointed out that the bizarre nature of neutrinos could be directly linked to the matter-antimatter asymmetry that allowed our universe to form. The leading theory suggests that neutrinos might be their own antiparticles, a class of particle known as a Majorana fermion. If this is true, a rare form of radioactive decay could occur, one where no neutrinos are emitted at all. This process, called neutrinoless double beta decay, would prove that a neutrino and its antimatter counterpart are the same thing. Experiments deep underground, shielded from cosmic rays, are searching for this incredibly rare event. Catching it would be like hearing a single pin drop in a roaring hurricane. It would not only explain the neutrino's tiny mass, but could also show us how these particles help tip the cosmic scales in favor of matter in the universe's first moments. The sheer smallness of their mass creates an infinity of questions on the quantum scale, a puzzle of fine-tuning that rivals the cosmological constant problem. How can something so insignificant hold the key to so much? This struggle to measure and define the properties of such an elusive particle leads us to an even deeper strangeness, the point where observation itself seems to shape reality. Reality itself seems to blur at the edges when we look too closely. The rules of the quantum world state that a particle, like an electron, does not have a definite position or state until the moment it is observed. It exists in a haze of probabilities, a superposition of all possible locations and conditions at once. This is not a limitation of our technology, it is a fundamental property of nature. But this leads to one of the most profound questions in all of science. What exactly counts as an observation? When does this probability wave collapse into a single, definite reality? Is it the act of a conscious mind perceiving it, or does the interaction with any larger object, like a measuring device, cause the collapse? This is the quantum measurement problem, and it is a paradox that places consciousness itself at the center of a cosmic mystery. Some interpretations, like the Copenhagen interpretation, simply accept the collapse as a fundamental process without a deeper explanation. But others take a far more radical approach. The many worlds interpretation, championed by physicists like David Deutsch, suggests that the wave never actually collapses at all. Instead, every single possible outcome of a quantum event actually happens, but each one plays out in its own separate, newly branched universe. In this view, the universe is constantly splitting into an infinite number of copies, a multiverse of all possibilities. Your decision to watch this video created a branch where you did, and another where you did not. This is not science fiction. It is a serious attempt to remove the arbitrary line of what constitutes a measurement by making infinity an inherent feature of reality. The implications for cosmology are staggering. It suggests that the entire history of our universe, from the Big Bang to this very moment, is just one thread in an infinite tapestry of what could have been. It forces us to ask if the laws of physics we observe are truly fundamental, or merely the local bylaws of our particular cosmic branch. This philosophical quandary inevitably pulls us back to the role of the observer, and whether a conscious mind is somehow necessary to bring the universe into being. This idea that consciousness might be a fundamental ingredient of reality is one of the most controversial in all of science. It suggests that the universe only takes a definite form when observed by a conscious mind, that reality is a kind of potential waiting for a witness. The physicist John Wheeler framed this with his participatory universe model, proposing that we are not just passive observers but active participants in bringing the universe into being. He famously illustrated this with his delayed choice thought experiment, where a decision made in the present seems to retroactively determine the past behavior of a particle. It is a mind-bending concept, implying that the entire cosmic history from the Big Bang onward might be shaped by acts of observation in the future. Most physicists, however, remain deeply skeptical. They argue that a measurement is simply an interaction between quantum systems, and consciousness has nothing to do with it. Labeling consciousness as the cause of wave function collapse is often seen as a retreat into mysticism, a failure to find a true physical explanation. This debate sits at the blurry boundary between physics and metaphysics, a place where the infinity of quantum possibilities meets the infinity of philosophical interpretation. It shows how our deepest unsolved mysteries force us to question not just the nature of the cosmos, but our own role within it. And if our local observations can ripple through the fabric of reality, then our entire galactic neighborhood is being pulled by a force we cannot see, a mysterious gravity well known as the Great Attractor. Our galaxy is caught in a powerful current, a silent river of stars and dark matter flowing toward an unseen destination. We are being pulled toward a mysterious region of space known as the Great Attractor, a gravitational anomaly so powerful that it draws our entire Milky Way and thousands of other galaxies toward it at over 2 million kilometers per hour. The problem is we cannot see what it is. This colossal mystery lies directly behind the dusty, star-filled center of our own galaxy, a region so obscured by cosmic debris that it is like trying to see through a dense fog. Our optical telescopes are virtually blind to it. For decades, this was a huge blank spot on our cosmic map. Astronomer Renée Cron-Courtoueg has dedicated her career to peering through this veil, using radio and infrared telescopes to map the hidden structures. What we have learned is both clarifying and deeply puzzling. The Great Attractor is not a single, unimaginably massive object. It appears to be the dense heart of the Laniakea supercluster, a vast web of galaxies that includes our own local group. But even that immense concentration of mass does not seem to fully account for the strength of the pull we feel. This suggests the flow extends even further, pulling us towards something even larger and more distant that we have yet to identify. This local mystery is a perfect miniature of the larger cosmic web, a reminder that gravity connects everything from our galactic neighborhood to the largest structures in the universe. And if our place in this flow is still uncertain, our position within an even grander cosmic emptiness is even more so. This cosmic flow is not the only thing pulling at us, for we may also be sitting in a cosmic emptiness. Our entire observable universe, all 100 billion galaxies of it, might be residing inside a vast and staggering void, a bubble of relative nothingness known as the KBC void. The name comes from the astronomers who proposed it, Keenan, Barger, and Cowie. This is not a simple gap between galaxy clusters, but a potential spherical region of space billions of light years across where the average density of matter is significantly lower than the rest of the cosmos. If this is true, it would have profound implications for how we measure the universe. The emptiness around us would act like a gravitational hill. As light from distant supernova travels out of this underdense region and into the denser universe beyond, it would gain a little extra energy, making those supernova appear slightly brighter than they should. We would then miscalculate their distance, and this error could trick us into thinking the universe's expansion is accelerating faster than it truly is. This single idea could potentially resolve the Hubble tension, that nagging disagreement between local and ancient measurements of cosmic expansion. But this solution comes with a massive cost. It would force us to question the cosmological principle, one of the most cherished foundations of modern cosmology. This principle states that on the largest scales, the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. A void of this immense size would violate that principle, suggesting our place in the cosmos is special, not typical. As cosmologist Robert Caldwell has discussed, this idea rigorously tests our deepest assumptions. Are we truly in a representative part of the universe, or are we living in a rare and quiet neighborhood, a cosmic backwater that skews our perspective? The possibility of an infinite cosmos filled with an infinite variety of such structures, both dense and empty, adds another layer of profound mystery to our maps. If our local void has shaped our view, then our understanding of the sun's own history might be equally skewed by a different kind of emptiness, one of energy from a fainter, younger star. Our sun was a faint, young star, radiating 30% less energy than it does today. By all rights, early Earth should have been a frozen ball of ice, a snowball world locked in a permanent deep freeze for its first 2 billion years. Yet the geological record tells a completely different story. Ancient rocks show clear evidence of liquid water and even signs of early life from a time when the planet should have been uninhabitable. This is the faint young sun paradox, a glaring contradiction between our understanding of stars and the history of our own world. How did Earth stay warm under a cooler sun? The most likely answer is a supercharged greenhouse effect, a thick atmosphere rich in potent heat-trapping gases like methane and carbon dioxide. But the puzzle deepens when we try to find the source of these gases. Was it constant volcanic outgassing, or perhaps the relentless metabolism of the earliest life forms already shaping the planet's climate? This paradox is not just about our past, it is a key to finding life elsewhere. As astrobiologist James Casting has long argued, understanding how a planet can maintain liquid water under challenging conditions is the central question in the search for habitable worlds. It forces us to consider complex planetary feedback loops where geology, biology, and atmospheric chemistry interact to create a stable environment against the odds. The faint young sun paradox is a stunning reminder that a planet is not a passive rock orbiting a star, but a dynamic system. It shows how the infinity of deep time allows for subtle, long-term processes to create stability from initial chaos, and it warns us that the conditions for life might be far more delicate and far more miraculous than they appear. The cosmos contains more planets than all the grains of sand on every beach on Earth. With such a staggering abundance of worlds, the silence from the stars is deafening. This contradiction is the heart of the Fermi Paradox, a simple yet profound question asked by physicist Enrico Fermi. If the universe is so vast and ancient, and if life is a natural outcome of cosmic chemistry, then where is everybody? The sheer scale of the galaxy suggests it should be teeming with civilizations, yet our telescopes have detected nothing but empty static. The solutions to this puzzle are as vast as space itself. One possibility is that Earth is extraordinarily rare, a perfect confluence of a stable star, a protective giant planet like Jupiter, a large moon to stabilize our axis, and plate tectonics to regulate our climate. This rare Earth hypothesis suggests that while microbial life might be common, the complex chain of events needed for intelligent, technological life is a cosmic fluke. Other ideas are far more unsettling. Perhaps intelligent life is common, but it inevitably destroys itself through war or environmental collapse before it can master interstellar travel. Or maybe the universe is simply too old, and any advanced civilizations that once existed have long since transcended to a state we cannot perceive or have simply died out, leaving us alone in the cosmic graveyard. There are even more speculative solutions like the zoo hypothesis, which proposes that advanced species are aware of us but have chosen to isolate us in a kind of galactic nature preserve, allowing humanity to develop without interference. As the pioneering astrobiologist Jill Tarter has often argued, our search has only just begun. We have barely scanned a few drops in a cosmic ocean. The absence of evidence is not evidence of absence. We are only now developing the tools to search not for radio signals, but for the faint traces of technology, the technosignatures that might reveal a civilization far older than our own. The search for intelligence beyond Earth has moved far beyond listening for simple radio greetings. We are now hunting for the faint, cosmic fingerprints of technology itself, signs we call technosignatures. Imagine not a message, but the silhouette of a vast solar panel array orbiting a distant star, or the unnatural chemical signature of industrial pollution in an alien atmosphere. These are the types of clues astronomers like Jason Wright are now pursuing, Our newest telescopes, like the James Webb, offer a revolutionary way to search. By analyzing the starlight that filters through the atmospheres of distant exoplanets, we can read their chemical composition. The telltale sign of chlorofluorocarbons, a human-made pollutant, would be a staggering discovery, evidence of a civilization that has altered its own world. We can even look for the unnatural dimming of a star that might suggest a megastructure, like a swarm of energy-collecting satellites, is orbiting it. Yet, despite scanning thousands of stars, we have found nothing. The sheer infinity of possible technologies and engineering approaches across the cosmos makes this search both thrilling and immensely daunting. An alien civilization 1 billion years older than us might use forms of energy and construction we cannot even conceive of, leaving signatures that are completely invisible to our current methods. This grand, silent search forces us to confront a humbling final question, a mystery that underlies all the others. Are some truths about the universe, especially those concerning other minds, fundamentally beyond our ability to ever know? Perhaps our universe is built on truths that are, by their very nature, unprovable. This is not a statement about our tools or our intelligence, but a deep feature of mathematics and logic itself. In the 1930s, mathematician Kurt Gödel delivered a stunning blow to the dream of a complete and perfect system of knowledge. His incompleteness theorems proved that within any sufficiently complex system of rules, like the arithmetic we use to count, there will always be true statements that cannot be proven using those rules. The system cannot validate itself. The truth is bigger than the proof. Now apply this to the cosmos. Our entire scientific method is a system, a set of rules for understanding reality. Could the universe contain truths that are real and factual, but that lie forever beyond the reach of this system? The ultimate nature of the multiverse, the precise reason for the Big Bang, the final explanation for why there is something rather than nothing, these might be cosmic versions of Gödel's unprovable statements. They are true, but we may never have the logical framework to conclusively demonstrate why. As philosopher Rebecca Goldstein has explored, this introduces a profound humility into our quest. Infinity is not just a physical concept, it is a logical one. An infinite universe might contain an infinite number of truths, and some of them could be permanently hidden from our finite methods of inquiry. This does not mean we stop asking questions. In fact, it makes the journey more meaningful. Every mystery we solve likely reveals a deeper layer of questions beneath it. The struggle to understand dark matter or the cosmological constant is not a path to a final answer, but an endless frontier of discovery. These unsolved theories are not failures, they are guideposts. They teach us that the universe is far more strange and wonderful than we ever imagined, and that our purpose is not to conquer the infinite, but to explore it with endless curiosity. The greatest discovery may be that the search itself is the point. From the invisible grip of dark matter to the infinite sprawl of the multiverse, these are the cosmic riddles that refuse to surrender. They are not failures of science, but its very engine, the perpetual frontier that pushes our understanding ever outward. Each unanswered question is an invitation to look deeper, to wonder more wildly about our extraordinary place in this vast and mysterious cosmos. As the great Carl Sagan once reminded us, somewhere, something incredible is waiting to be known. So keep questioning, stay endlessly curious, and let us know which of these mysteries captivates you most in the comments below. If you enjoyed this journey to the edge of understanding, be sure to subscribe for more explorations into the unknown. Thank you for watching, and may your curiosity always reach for the stars.